Hello, welcome to Unit 5 of AP Calculus. I'm calling this unit Applications of the Derivative Part 1 because there's also a Part 2. But we've actually already seen an application, a very important one, in the form of related rates. Now, the related rates I would call an application of implicit differentiation, whereas in this unit we're going to focus on the application of just derivatives of explicit functions and maybe tie it back to implicit here and there. This is probably, and I'd have to double check, but I'm fairly certain that the lion's share of the AP exam material that's tested will cover this unit. Of course, all units of study get covered on the AP exam, but on the AP AB exam, you're going to expect this unit to hit the hardest. So let's really buckle down and pay attention. In this lesson, we're going to be learning about one of the most important theorems in the history of mathematics, the mean value theorem. We'll actually learn two theorems, and we'll start with the Rolle's theorem. Okay? So I want you to consider these following differentiable curves. We're going to look at just a few of them, okay, over some closed interval a to b. So let's start with these two here. Just kind of look at them and notice what we're saying about a and b, that f of a is equal to f of b. And then down here. And the question I have for us is, based on the graphs and your own intuition, what value can we conclude the slope of the tangent line must achieve at least once on the interval from a to b? So let's go back and look at this one. We're looking for a special value that the derivative must take. Well, if you look at the first graph, if we are the same height here as we are here, then the graph would have to at some time come back down. You know, it's kind of like what goes up must go down. And that this, somewhere here, there's got to be a horizontal tangent line. Let's take a look at this next one. From A to B, now this time the graph is going down. You know, if we know that f of A is equal to f of B, well, as long as it's now, you know, whether it's going, the graph is going up or down doesn't matter. We know that whichever direction it's going, it has to come back because we know that it comes back to the same y value. So it must have a place where it turns the corner, a place where the tangent line is horizontal. Now, if we look at this one, it turns out that there's actually a couple of places, right? Because it turned out that it went up. We know that if f of a equals f of b, then what goes up must come down. But it turns out that it already hit right here and came down again. And then came back up. So there was two of them. So knowing that f of a equals f of b doesn't mean that there's exactly one place where there's a horizontal tangent line. It just means that there's at least one place. So let's just answer this question. Based on the graphs, we can say that the slope of the tangent line must be 0. That's a horizontal tangent line when the slope is 0. Is the differentiability of f required on the entire interval from a to b? Well, we said they were differentiable. Well, do they have to be differentiable in order? Is that an important statement? Well, let's think about it. Could I draw a graph where f of a is equal to f of b, but the horizontal tangent line never occurs? Let's see if that's possible. So I'm just going to call this here is going to be a. Okay, so that's going to be f of a right there. And I'm going to call this b. That's going to be f of b. Okay, so this is a, b. And then this here is both f of a and it's also f of b. Well, I think clearly if I go up here and I have an asymptote in the middle of this thing, that I could come back from below like this and never actually equal 0. So we definitely need continuity, which differentiability does say. But let's say that it is continuous but not differentiable. Well, if you give me that, if you say that it has to be continuous but doesn't necessarily have to be differentiable, then I can do something like this. And that curve never actually has a horizontal tangent line. It has an undefined derivative right here where it makes a cusp. So in order to be certain that the tangent line does equal 0 at some place, we'd have to know that the line was differentiable everywhere on that interval. The curve was differentiable, excuse me. Okay, so this brings us to Rolle's theorem. If a function f is continuous on a closed interval from a to b, differentiable on the open interval from a to b, and f of a equals f of b, then there exists at least one value c on the open interval from a to b such that f prime of c equals 0. So you'll notice I have a little thought bubble here. And what that thought bubble is reminding us is that Rolle's theorem requires CCDO. So CCDO stands for continuous on a closed, differentiable on an open. And that's just kind of my little trick to remember it. CCDO. And remember what all this is saying. It's saying that if f of a equals f of b, you're continuous and differentiable, then whatever goes up must come down, whatever goes down must come up. So we have to have that horizontal tangent. Let's take a look at an example. Determine whether the conditions of Rolle's theorems are met for the stated interval. If so, find the value c that Rolle's theorem guarantees. All right, so we're going to first see that the conditions apply. We have to show that we're continuous on a closed and differentiable on the open. So what that means is you don't necessarily have to be differentiable on the ends of this interval, but you have to be differentiable on the inside. So this is a polynomial, and polynomials are continuous everywhere. So we're just going to go ahead and say that f is continuous on the closed interval. And because it's a polynomial, I can also show that it is differentiable. One way to show that something's differentiable is to simply take the derivative and show that the derivative is continuous on that interval. Well, 2x minus 1 is continuous everywhere. So we're going to say f is differentiable on the open. And I'm going to require you to get that right. You need to show me that it's closed on a continuous interval, and it's continuous on a closed interval and differentiable on open. Make the distinctions. Okay, so now that we've got that, we also need to show that f of negative 2 is the same as f of 3. Well, f of negative 2 would be 4 plus 2 is 6 minus 6 is 0. Okay, let's find out what f of 3 is. Well, that would be 9 minus 3 is 6 minus 6 is also 0. So because those are equal, we're going to cite this theorem. We'll say by Rolle's theorem, f prime of x must equal 0 for some x on the open interval from negative 2 to 3. Okay? We know that's true. And I ask us to go ahead and find that value just for fun. Although usually in these applications, you either can't find it or you don't need to find it. But let's go ahead and find it. I'll just move that down. We already found f prime, so let's set it equal to 0. So 0 equals 2x minus 1. 1 is equal to 2x, so x is equal to 1/2. And is 1/2 on that interval? Yeah, absolutely. So, in that case, it was probably easier to just find the x value than to actually use the theorem. But like I said, usually the case is that you can't for some reason. So, but I did want to have us solve it to confirm, sure enough, that that value does exist and it is on that interval. All right, let's take a look at this one now. Move all these down a little bit. All right, we need to see that the conditions of Rolle's theorem are met. First of all, we need to conclude that f is continuous on a closed and differentiable on an open. CCDO. Let's go ahead and take the derivative. The derivative of tangent u is secant squared u prime. Well, let's see here. F is f continuous on the interval from 0 to pi? Well, no, it's not, because tangent of pi over 2 is undefined. So I'm going to say f is not continuous on this closed interval. So Rolls does not guarantee that. So Rolls does not guarantee that f prime of x equals 0 on this interval. Absolutely not. Could it? Well, sure, it could. Rolls doesn't say it won't. It just says that it just can't say that it does. I think, in fact, tangent of x on 0 to pi, I don't think it does at all, actually, ever equal 0. So, yeah, no, we can't. That doesn't happen. And, all right, let's try this next one. Okay, let's take the derivative. We'll need that. That's 2/3 x to the negative 1/3. All right, well, clearly y is continuous. I'll just abbreviate on this closed interval, yeah. But because this is a negative exponent, this is really equal to 2/3 times, like, you could say the cube root of x. 0 would make this undefined. So y is not differentiable on that open interval because 0 is inside this, is in this open interval. So we can't use that. So again, Rolls does not apply. Could it? Sure. We can't use Rolls' theorem to confirm it. I actually think this one doesn't. So that would definitely give us a wrong answer if we tried to use that. All right, let's take a look at a table now. The following table shows the values of a twice differentiable function at x of t, which models the position of a particle moving horizontally along the x-axis, and v of t, the velocity of the particle at various times t. Recall that v of t is equal to x prime of t. So that's just there for our notes. We wouldn't normally expect anyone to tell us that, right? All right, at least how many times must the position of the particle be equal to 40? Okay, so the position of the particle, that's this. This is the position function. All right. Well, I see that x of 31 is less than 40, and x of 42 is greater than 40. I also see that x of 42 is greater than 40 and x of 50 is less than it. So as long as I can say that x is a continuous function, we can conclude that this must have indeed be equal to 40 at least twice. Maybe it goes up and down a little bit in between here. We don't know, but we know that it has to happen at least once in this interval and another time over here. So can we say that x is continuous? Well, I can, because it says it's twice differentiable. So twice differentiable means that you can take the derivative of it twice and it's continuous everywhere. So twice differentiable, so we'll just say that x, I know it's confusing to write x as a function, but I want you to get used to that idea that becomes very important. X of t is the position on a horizontal line of motion. So x is differentiable because you told me. Therefore, x is continuous. So we know that it's continuous, right? So we can then say, by the intermediate value theorem, x of t will equal 40 at least twice. I'm going to underline something right quick. This has to be there. That's a point. This part here has to be there. That's another point. This has to be there. This could totally be a 4-point question on a free response or anything like that. It could be worth 2, 3, 4, depending on how they want to count it, because there's so many different parts. There's the conclusion that yes, it can happen twice. They are citing the MVT, citing that it's how you know it's continuous, and of course showing these conditions. Really important, so we need to practice that every time. Next question. Must there be a time when the velocity of the particle is equal to 0? Well, let's take a look. Well, I don't see any time when the velocity is negative and then positive. So I will not be able to use the IVT to conclude that the velocity is 0. We just don't have that. However, maybe I can use Rolle's theorem. Well, if I look at this here, I can see that that x of 31 and x of 50 are equal. So I'm going to say that x of 31 is equal to x of 50. And I know that x is continuous and differentiable because x is differentiable. So therefore, and you've got to cite it. You got to say by Rolle's theorem. That's one of those theorems we have to know. By Rolle's theorem, x prime of t, which is equal to v of t, must equal 0 somewhere, I'll just say somewhere, on the interval from 31 to 50. Has to happen. Has to. Even though we don't have that enough data to use mean value theorem, it has to happen. I mean, we don't have enough data to use intermediate value theorem. We're about to learn the mean value theorem. All right. Okay, Rolle's theorem can be generalized to form the mean value theorem. And the mean value theorem gives us a lot of power. In fact, I could do the question that we just did using the mean value theorem as well. And we could use it in combination with the intermediate value theorem and get a lot of information. So let's learn the mean value theorem. The mean value theorem says that if a function is continuous and differentiable, then there is at least one value c on the interval from a to b such that f prime of c is equal to f of b minus f of a over b minus a. Note that the MVT, not the IVT, the MVT also requires CCDO. And in fact, I want you to understand that you can think of Rolle's theorem as simply a special case. If f of b and f of a are equal, like they had to be in Rolle's theorem, then you have 0 on top of something that's not 0. So that would mean that you have 0. F prime of c equals 0. This is just saying that, hey, in that case, the secant line was horizontal. But in the more general case, any secant line, we can say this. All right, so what exactly does this mean? Well, in other words, as long as f is continuous on the closed interval from a to b and differentiable in the open interval, there must be a place where the slope I'm having trouble reading what those blanks were supposed to be. Let me look on these notes over here. Where the I just got kind of cut off. The slope of the tangent to f is parallel to the secant line. That's what I want to say. Okay, hold on. Let's go back and say that again. Because I could say it so many different ways. I wasn't sure what kind of blanks I was trying to do because I couldn't see how many there were. All right, that makes sense. In other words, as long as f is continuous and differentiable, there must be a place where the tangent line to f is parallel to the secant line from a to b. So let's take a look at a picture. Okay, so the mean value theorem says if I have an x value at a, right here at a, and I have another x value here at b, then I can find the slope of the secant line, or what we call the average rate of change, right? This is the average rate of change to a and b. Well, there must be a place somewhere on this curve where the tangent line is parallel. So I hope you see that this is why I meant that the Rolle's theorem is simply a special case. If I do this again, and let's take a look at it as if it was Rolle's theorem. if I had a problem like this, right? And let's say this was our A and this was our B. Well, then what we're saying here is that the secant line from A to B, because they're equal, is horizontal. And so there must be a tangent line that's horizontal. So this is just a generalization of it, that we know that there must be a place where the tangent line is the same, is parallel to the secant line. Or in other words, this slope is the same as this average slope. All right, now here's the formula that I typically tell people to memorize. Let me just copy that right quick so that you can see how compare these two things here, see how they relate. So this is the formula that I talk about on the bottom, but you should be able to understand that I could easily multiply both sides by b minus a and get this. This ends up being a very important theorem. It's talking about the change from a to b. There's another way. There's lots of manipulations and ways we can say the mean value theorem, and you just want to be comfortable algebraically transforming to different ways of looking at it. All right, let's do an example. We got a function here. F of x equals 3 minus 5 over x. I went ahead and graphed it for us. And we have to draw the secant line from x equals 1 to x equals 5. Well, so here's x equals 1. It's down here. This is 1 comma negative 2. And then 5. 1, 2, 3, 4, 5. And this is 5 comma 2. All right? So let's draw the secant line there. Okay. Estimate the location of the value guaranteed by the mean value theorem. Well, the mean value theorem says there must be some x value, at least one, maybe more than one, where the tangent line would be parallel to this. And I'm going to just estimate it somewhere around there. All right, I'll tell you what, let's go find it. Let's find that value. Demonstrate the mean value theorem applies. Okay, does it apply? Is f continuous? Well, we need to be careful because there's a division by x, but that would only be discontinuous at 0. So I think we're good from 1 to 5. So I'm going to say f is continuous on the closed interval from 1 to 5. Let's find the derivative. The derivative f prime of x is equal to 5 over x squared. Because this is 3 minus 5x to the negative 1, so I bring down the negative 1, it becomes 5x to the negative 2. So I'll just write it like that. Well, same issue here. We can see that it would be discontinuous at 0, but the derivative is continuous from 1 to 5. So I'll say f is differentiable. I know I'm abbreviating here. I hope that's okay. On the open interval from 1 to 5. And that's it. That's all I need to do to establish the mean value theorem. So we know that f prime of x somewhere on that interval must be equal to the slope of the secant line. That's what mean value theorem says. Let's write it, that f prime of x will equal to f of b minus f of a over b minus a for some x in between a and b. Well, the slope here, we can easily get f of b is 2, and f of a is a negative 2, right? Over 5 minus 1. So this is 4 over 4. Well, that's just 1. I think we could say that's up 1 over 1, up 1 over 1, right? Okay. So what we know is that this somewhere must equal 1 on that interval. Well, I'll multiply both sides by x squared, and I get 5 equals x squared. Take the square root, and we get plus or minus the square root of 5 equals x. Well, what was the value that was guaranteed by the mean value theorem? We need to be careful about this, right? Well, the value that was guaranteed by the mean value theorem is the positive square root of 5. That's the value that was guaranteed. So if they ask for that, you don't give them one that's not in that interval. Square root of 5 is, in between 2 and 3. So definitely it's on the interval from 1 to 5. All right. Looks like we got some practice problems for you to do. So I want you to do practice problem 1.1, and then we'll talk about it. All right, let's see how we did. We're going to show that the MVT value theorem applies, and we'll find it. So looks like I got a graph here. That's kind of nice, from interval of negative 2 to 2. All right, well, let's get the derivative first. Okay, there we go. So f must be continuous to use the mean value theorem. F is continuous on the closed interval. Very good. Okay, f is differentiable on the open interval. Okay, I like it. So we know that the mean value theorem guarantees there's a value on the open interval of -2 to 2 where this equals the slope of the secant line. So let's get the slope of the secant line. So f prime of x must somewhere equal f of b minus f of a all over b minus a. So we get f of 2. 8 minus 6 is 2. F of -2. Well, that would be a -8 plus 6, so that would be a -2, which makes that plus 2. All over, we're doing 2 minus a -2, so 2 plus 2. Well, that's just 1 again. Not too bad. All right, let's solve our derivative equal to it. Okay, I get 3x squared equals 4. So x squared is equal to 4/3. So x equals plus or minus 2 over the square root of 3. Square root of 4 over the square root of 3. And it needs to be on the interval from -2 to 2. Are they both on that interval? Let's see here. 2 divided by the square root of 3 is a number a little less than 2. So that would be like positive 3-ish. No. What would that be? You know what? I'm going to simplify the radical. It's making it difficult for me to do. So 2 root 3 over 3. Let's see, what would that be? 2/3 of the square root of 3. So that's definitely less than 2. So I think both of these values work. So I'm going to say plus or minus 2 over the square root of 3 are the values. Guaranteed by the MVT. Okay. Yeah, you know, it's kind of makes sense if you think about it. We've got this picture here. It doesn't really show the units so much. The zeros would have to be at plus or minus the square root of 3. So we said, what did we say? It was like -6 on one, and then positive. No, it was 2 and -2. Okay. So it's probably something like this, you know. And I think that we could see that there would totally be a couple places where that would be parallel. Okay, time for me to do another one. Given that f of x equals cosine 2x plus x, what is the slope of the secant line from -π/4 to π/4? Okay, well, we can do that. That's not too bad. We have to find f of b minus f of a over b minus a. That's the slope of the secant line. So that's f of π/4 minus f of -π/4 all over π/4 minus a -π/4. So it's plus positive. All right, f of π/4. Well, that would be the cosine of π/2. The cosine of π/2 is 0, so it's just going to be π/4. Cosine of -π/4 is also 0, so this is just a -π/4. So it ends up being that as well, plus a positive. And we can see that we're just dividing the same thing by itself, so it's 1. That's the slope of the secant line. Let's determine if means or Rolle's value applies on this interval. Well, we just showed that f of π/4 is equal to f of -π/4. That's what we got, right? Oh, no, it wasn't. It was not. Okay, never mind. That would be if we got 0. We didn't get 0. Never mind. Sorry. I was just thinking because each time it was something with π/4, but one was positive, one was negative. So no, we can't use that. But we can say we can't use Rolle's, but we can use the mean value theorem because we can say that f is definitely continuous on the closed interval from -π/4 to π/4. And let's get the derivative of f. So f prime of x is equal to negative sine 2x times 2. So I'll just say a -2, then plus 1. That's continuous everywhere as well. So f is definitely differentiable on the open interval for sure. And we said to solve this equal to 1. Well, if I solve it equal to 1, it actually becomes kind of an easy problem. Because the 1's will go away, and I get 0 equals -2 sine of 2x. So that means sine of 2x equals 0. So when does sine equal 0? Well, sine is equal to 0 at 0 and pi and negative pi. If I divide pi by 2, I'll get pi over 2. That won't be in the interval. So it's just x equals 0 is the value. That's the value guaranteed by the MVT. All right, got another practice problem for you to do. Give it a shot. All right, let's see how we did. A cat hears something in the middle of the night. The cat decides to jump up with a crazed look in her eye and starts streaking back and forth in a horizontal manner down the hallway. The cat's position is modeled by the twice differentiable function c of t. The cat's position in feet is and velocity in feet per second is shown in the table below. There seems like there's an extra word. The cat's position in feet and velocity in feet per second is shown on the table. Okay, so we have position and the velocity. Right, this is a derivative of that one. Estimate the cat's acceleration at time t equals 6. Show the calculations that lead to your proper show your calculations include proper units. All right, we know that acceleration is the derivative of velocity. So this is just asking, so the acceleration of the cat is equal to v prime of the cat, right? So let's take a look at v prime of 6. Well, we can estimate that. We have 6 is in between 5 and 8, so I'm just going to do v of 8 minus v of 5 all over 8 minus 5. Well, v of 8 was 5. V of 5 is 12, and 8 minus 5 is 3, so that's let's see here, negative 7/3. So we can estimate that the cat was traveling negative 7/3 feet per second so feet per second squared. That's the acceleration. I want to remind you how you get the units on the derivative. When you have the units to the derivative, we're taking this is my y value and this is my x value, if you want to think of it that way. The derivative is always the units on y over the units on x. So I have feet per second over second. You can write it that way, feet per second over second. We usually write feet per second per second. Okay. For 8 less than or equal to t, less than or equal to 10, must there be a time when the cat's velocity was 4 feet per second? Must there be a time when the cat's velocity was 4 feet per second? Well, we don't have that. If I had something that was below 4 and above 4, I would definitely throw out the not throw out, but throw in the IVT. That would be really nice and easy. We don't have that, but maybe we can use the velocity. We can maybe establish a velocity of 4 using c of t. So this could be easier or harder depending on how this goes. If we can establish using the mean value theorem that there's a time when the velocity was below 4 and another time using the mean value theorem where the velocity is above 4, we can then combine that with the intermediate value theorem, since we know that the velocity is continuous, to say that it must have equaled 4 in between there. So be on the lookout for that. But we're going to look and see if we can't get a slope of 4 anywhere on here. So let's see here. From 30 to 20 is a change of 10 over 2. That's 5. That's not good enough. All right. Well, let's see here. We've got from 4 to 12 is change of 8. 8 over 2 is 4. So yeah, that we got it. We got everything we need right there. So we need to set up. We're going to be using the mean value theorem here. Okay. So we know that C of 10 minus C of 8 over 12 minus 4, that is equal to 4. Wait, minus, no, I've done, sorry, ignore what I just said. I put down the values. Over 10 minus 8. Well, that was equal to, C of 10 was 12, C of 8 was 4, over 10 minus 8. That's 4. We know that. Well, we got to remember, what does the mean value theorem require? CCDO. CCDO. Live it and love it. Continuous closed, differentiable open. Well, what do we know? We know that this function is twice differentiable. So C is differentiable and therefore continuous and differentiable. And I know you can't read my little pen scratch, but it's difficult to write on a computer. We're going to cite our theorem by the MVT. C prime of t, which is equal to v of t, must equal 4 for some value t on, well, I'll say it like this, greater than 8 and less than 10. It's got to happen. Oh, they gave us the 8 and 10. Here I am searching through. They gave us the 8 and 10. That was nice. I didn't even look at that. All right, moving on. For t between 3 and 10, how many times must the velocity of the cat be 0 feet per second? So how many times must the velocity be 0 feet per second? Well, we know that the velocity would be 0 anytime we could establish that C of A equals C of B. Does that make sense? I can use Rolle's theorem. If I can find two A values and say that C of A is equal to C of B, then I can use Rolle's theorem, right? Well, we know that you can't, if C is continuous, I can't go from 30 to 4 without equaling 20 somewhere, right? That's got to happen. So I'm going to say that C of, what was it again? C, actually, what I'm going to do, I'm going to copy this and bring this down so I don't have to keep going up and down. All right, so I can get rid of that later, but we're saying C of 5. C of 5 is greater than 20. And that's greater than C of 8. Okay? So, and I'm going to mention that C is continuous because it's differentiable. So by the MVT, C of t equals 20 somewhere. I don't want to say on, that makes it sound like everywhere. Somewhere on the interval from 5 to 8. Has to. Okay? So that's one place where we know it happens. Well, where's another place? Let's see if we can't find another place. So we know it happens somewhere in here that we're equal to 20. So therefore we know that somewhere between 3 and 8, it's got to happen that we have that derivative equal to 0. Well, you know, if you look here, this is 4, and then later on we become 12. So somewhere in between 8 and 12, well, I don't know if we could say that again. Does that help us at all? Can we get anything else? I don't think we can. Let's see here. We know that we're going to be 0 somewhere, and then we're going to go back up to 5. It could go down and I think just kind of glance at 0. No. We can say something else here. The velocity has got to be negative somewhere. There's no way that these feet could go down without it being negative. So if it's actually going to go down negative, we know it's got to come back up to positive. So we could say that. I'm going to say that C of 8 minus C of 5 over 8 minus 5 is definitely less than 0. That's definitely a negative number because that's 4 minus 30. So we know somewhere up here we equal 0. Then we become negative. And then check this out. I could say C of 10. This might have been easier to do this from the beginning. C of 10 minus C of 8 over 10 minus 8. Well, that's a positive number. So let's see here. We have a value where equals 0. Then we go negative. Then we go positive again. So we must have hit 0 at least twice. At least twice, because we got a positive value for we know that we have a positive value for the velocity. Then we have a negative value. Then we have a positive value again. We had to have hit it at least twice. I'm not really going through that as thoroughly as I should right now, but we'll just leave it. The table below shows the number of vehicles stopped at a busy intersection in a city over the course of 8 hours. So go ahead and do this problem right quick if you haven't yet. Okay, let's see how we did. The table below shows the number of vehicles stopped at an intersection over the course of 8 hours. The number of vehicles at time t is modeled by a twice differentiable function v for 0 less than or equal to t less than or equal to 8. Values of v of t at various times t are shown in the table. Use the data, the date. Use the data to estimate the rate at which the number of vehicles was changing at 4:30. That's t equals 4.5. So we'll have to use 3 and 5. Well, we could do that. So the rate the number of vehicles were changing, this is the number of vehicles, so the rate they're changing is their derivative. Is going to be, we should really say approximately v of 5 minus v of 3 all over 5 minus 3. So that's, you have to plug in, though, 103 minus 80 over 5 minus 3 is 2. That's kind of the rules. So we got that. Just for fun, we'll just say that's 23 over 2. Okay, so 23 over 2. The units, remember, it's anytime you take a derivative, it's the y units over the x units. So it's people per hour, right? Well, it should really be vehicles per hour. I was thinking of people in the vehicles. Yeah, I'm going to say vehicles per hour. Sorry, I make these up. Sometimes they have bugs in them. You can excuse it, right? For 0 less than or equal to t less than or 8, what is the fewest number of times v prime of t must equal 0? What's the fewest number of times that v prime of t must equal 0? Well, let's see here. We got 60 to 51. That's a negative number. So I'm going to say that v prime of t is negative somewhere on the interval from 0 to 1. Because that's a negative number, right? We can find out exactly what it is by using the mean value theorem. Okay. Now, what else do we know? Well, the v prime of t is greater than 0 somewhere on the interval from 1 to 3, because that's a positive velocity. And then again, we get that v prime of t is less than 0 somewhere on the interval from 5 to 6, because that's negative, right? And then possibly stays negative. So we have a negative number, then a positive number, then a negative number. So v prime of t is equal to 0 at least twice on the interval from 0 less than or equal to t less than or equal to 8. We're going to go ahead and say a couple things. We will say that v is differentiable and therefore continuous. All right. And we're able to establish that we went from negative to positive. So we can say that we know this is by the MVT. And so there we could say that v prime t equals 0 at least twice by the IVT. So I use the IVT to establish that because it went from negative to positive number, I must have gone through 0. Then it went from a positive to negative, I must have gone through 0. I use the MVT to get those values when that happened, because I didn't have Rolle's theorem here. I didn't have something exactly giving me us, two y values the same. All right, let's go on to the next one. Let f be the function given by x cubed minus 3x squared for what value of x in the closed interval from 1 to 3 does the instantaneous rate of change of f equal the rate of change of f in the interval. So we just need to find when does the instantaneous rate of change equal the average rate of change. So that is asking us to use the MVT, right? So the average rate of change is f of 3 minus f of 1 over 3 minus 1. So f of 3 is 27 minus 27, that's 0. F of 1 is 1 minus 3, that's a negative 2. All over 3 minus 1, so that's 2 over 2 equals 1. I've seen that a lot. The instantaneous rate of change, f of x, is 3x squared, f prime of x, excuse me, is 3x squared minus 6x. So the question is, when does 3x squared minus 6x equal 1? So that'd be 3x squared minus 6x minus 1 equals 0. Just making sure I did all that right. 3 squared is 27. Yeah, that's definitely 0. And then 1 would be 1 minus 3. Okay. Okay. So it looks like we're going to have to use the quadratic formula. X equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. All right, so this is 36 plus 12, which is 48. So 6 plus or minus the square root of 48 all over 6. We need to be careful, though. What was our interval? 1 to 3. Square root of 48 is something between 6 and 7, really close to 7, actually. So if I do 6 minus 7, that's going to be a negative number. So the value that we're looking for is 6 plus the square root of 48 over 6. X equals that is where... And what did they ask us specifically to say? Where instantaneous okay. I think you know what I'm trying to say. It's very difficult to write without this thing bleeding over. Instantaneous rate of change is equal to the average rate of change over, what were we doing, 1 to 3? Change over 1 to 3. All right. And I think that's it for this lesson. So until I see you in the next one, take care.